All right, today we're going to pull back the curtain on a high stakes industrial mystery. It's this quiet little problem that ends up costing manufacturers an absolute fortune, and it's hiding in plain sight on some of the most advanced production lines you can imagine.
To really get this, just stop and think for a second about the amazing materials that make our modern world even possible. We're talking about components where there's zero room for error. The smallest little mistake can cause the whole thing to fail.
I mean, think about the super thin films that go inside an electric vehicle's battery, or the specialized glass on the smartphone that's probably in your pocket right now, even the packaging that keeps your food fresh, or the substrate at the heart of a solar panel. Every single one is a marvel, and they all have to be perfect.
So what's the common link here? What ties a car battery to a phone to a solar panel right back at the very beginning of how they're made?
Well, here's the answer. They all start out as these gigantic rolls of material, sometimes miles and miles long. And somewhere on these massive rolls, one tiny, almost invisible defect, a pinhole, a little bubble, a scratch, can completely ruin the final product. But you know what? The real problem isn't just finding the flaw, it's finding it again after it's been rolled up.
And this, right here, is what the industry calls the lost defect problem. So, a fancy vision system might spot a fly flying by, but as soon as that material gets wound up, cut, and processed, the exact location of that tiny little flaw is, well, it's lost. It's like trying to find one specific grain of sand on a really, really, really long beach.
For years, people have tried to solve this with some, let's say, pretty old-school methods. You've got encoder counting, which is basically a digital measuring wheel, but it tends to drift over time and lose accuracy. Then there are physical tags and flags, which, you guessed it, fall off or get lost when the roll is cut. And of course, ink marks, which are just messy and totally depend on someone not making a mistake. They all fail for the exact same reason. They treat this giant rolled-up thing like it's just a simple, straight line.
But what if that was just the completely wrong way to think about it? What if the answer wasn't a better ruler, but a totally different way of looking at the roll itself? This is that aha moment. It's about shifting your thinking from a ruler to something more like the rings of a tree. So the old way, linear tracking, it's just like using a measuring tape. The second you cut that tape, you have no idea where you are anymore. But this new idea, radial tracking, that's totally different. Think about the grooves on a vinyl record. The position of a song isn't measured from the beginning of the vinyl, it's physically part of the grooves. Each layer, each ring, is its own unique address. And this new concept has a name. It's called radial positioning. So instead of asking, how many feet from the start is this defect, you ask, on which specific wind, which layer, counting out from the very center, is this defect? Suddenly, that location is literally baked into the physical structure of the roll. And this quote just nails it, right? It says, traditional systems measure linear distance, but roll-to-roll processes are inherently radial in structure. It's so brilliant because the processes that make these rolls are already radial. They wind material layer by layer. So why on earth weren't we using a tracking system that matches that physical reality? The solution was literally hiding in the geometry of the problem the whole time. Okay, so we have this amazing idea, but how does it actually work on a factory floor with machines running at incredible speeds? Well, it all builds into this really slick, automated workflow. The process is actually pretty simple, but so powerful. The motto is, map it on the rewind, remove it on the unwind. So first, a high-speed camera detects a defect. Instantly, the system maps that flaw, not by how far it is from the start, but by its unique radial spot. This digital map then tracks the material no matter where it goes. And finally, when it's time to actually use the material, the map tells the machine exactly where to go to automatically remove only the bad section. Nothing more is wasted. Now, this isn't just some cool tech for the sake of tech. It has a massive real-world impact. We're talking about tangible savings in money, in materials, in time. So let's actually look at the payoff. For these industries that produce huge volumes, a 1 to 3% improvement in yield, that's enormous. I mean, when you're making millions of square feet of this stuff, saving that 1 to 3% that used to be scrapped just because you couldn't find the defect again, that translates directly into hundreds of thousands, sometimes millions of dollars saved every year. And the benefits just keep stacking up. Scrap gets slashed because you're only taking out the tiny bit that's actually bad. Customer returns go way down because now you can give them a digital, evidence-based quality report for every single roll. Your labor costs drop because you don't need people standing around putting on tags or watching for ink marks. And when a problem does pop up, finding its source is way faster because you can pinpoint the origin of a defect in an instant.
But honestly, the long-term impact of this technology is even bigger. It's about more than just finding flaws. It's about completely changing what a roll of material even is.
And this is really the big picture here. Radio positioning turns a simple, passive roll of stuff into an active, data-bearing asset. The roll now has its own digital identity, its own built-in map. Layer by layer, it knows its own history, its own quality.
And this just blows the doors open for the next generation of smart manufacturing. You can get true roll genealogy, perfectly tracing material from a giant mother roll down to every smaller daughter roll. It lets you create a true digital twin, a virtual copy of the roll you can use for all sorts of analysis. And all this data is the fuel for predictive analytics and, down the road, fully autonomous quality control. So let's just end on this thought. What happens when every single component in a supply chain, starting with that first roll of raw material, can tell its own complete detailed story? We're talking about a shift from just making things to making things that know themselves. And a change that big, well, that changes everything.